out in the middle of nowhere, a massive object, you essentially have two types of energy. You have the gravitational potential energy, and then you have its kinetic energy. So the kinetic energy is going to have the same form that we saw previously. It's the 1/2 mv squared. So it's not going to like magically change. And we know that the mass is not dependent upon the gravitational field, but the potential energy itself is going to change. So we can no longer just use mgh, because that only works when we're on Earth. What's up, Mitchell?
Couldn't when Newton like figured this out, couldn't he only do it with like individual ones? He couldn't do it for like a whole system and find out all the different relationships you want to know?
So multiple objects or multiple body problem. Yeah, so that, and even within here, we only look at one mass versus another mass. We don't look at the entire system. So if I tell you like, okay, figure out the gravitational potential energy at Jupiter with respect to all of its moons in it, it would become very messy. So we'll only just say,
do we ever learn that physics? If we ever
you will, but you won't learn it unless you're like, I'm going to be a physicist. Yeah, as an engineer or mathematician, you won't. But if that's like your burning desire, you want to figure that out by the time you leave this planet. Then, yeah. All right, so let's go ahead and look at what happens with the gravitational potential energy. So again, we're going to make it nice and simple. Just two objects impacting each other. We're not going to have 3 objects, 4 objects, 10 objects. In the case of Jupiter, if we had to look at all of its moons, I think it has 62 moons. That would be hecka messy. Yes, Mr. Kelly.
Is it possible to calculate a supernova?
What do you mean by calculate? Calculate what?
The force, the exerted from the supernova.
You can figure out the energy.
Oh, where did that come from? I was just thinking.
All right, so let's go ahead and look at, so I say recall, so somewhere floating around in the gray matter, I told you that,
Where did we get an upside down triangle?
I told you about the upside down triangle. It's the 3-dimensional dx, dy, dz, ddx, ddy, ddz. It's been a while. The last time we talked about it was when we talked about springs. So the force and the potential energy are related in such a way that the force is equal to negative the derivative of the potential energy. Okay? So if we were to go back to our springs, right? The force due to a spring was?
1/2 delta x.
Delta x.
Times negative. It's negative. There's k somewhere.
Negative 1/2 k delta x squared.
Squared. Something squared.
Negative k.
X is.
Negative k delta x. And so, if we wanted to figure out the potential energy for a spring, what would we have to do? We wanted to solve for u. And this is for a spring. This is just.
Now I know something squared this time.
So if I wanted to figure out u from there.
It'd be 1/2 k delta x squared, right?
Yeah, but how could I figure it out from there? What I'm asking you is, if I know that f equals this, how can I solve for u?
Divide by negative delta upside down delta.
By the triangle.
Divide by the triangle?
The negative triangle.
So when we're in our calculus class and we have f equals, we just divide by d dx and that's how we get it?
Take the integral.
That's all we do? We don't even integrate, we just divide by d dx?
You take the integral.
Yeah, so we have to integrate, right?
Oh man.
You write it as dx. Yeah, I got you. I'm sorry.
There, so I rewrote this as this, but just know that this means it's d dx, d dy, d dz.
Where'd you get it?
So I just used one of them. Okay? So how can I solve for u here?
Take the integral.
take the integral, right? So we integrate both sides. So if I integrate this side is just going to be this. So the force due to gravity is what? It's like double jeopardy question.
U squared over 2.
Big G
I don't know.
times M1, M2 divided by R.
Alright, so FG is
F big G.
GMM over R squared.
Yeah. Last week it's on.
Right?
Okay, so then you just want to plug in?
So we're going to plug this in. Now this is me just writing this. I did this poorly. This should have been an R, right? Because we have an R here.
And put it as
So if we have this, all right,
Wouldn't it
so
be
that
negative?
gives us the integral of GMM over R squared dr equals this.
Wouldn't it be negative U x?
So the G and these M's have nothing to do with the radius. So they come out of the integral.
The constants, kind of.
Whether or not they're constants, they have nothing to do with the radius. So even if they were spatially dependent upon something, they
take stuff with respect to stuff.
take stuff with respect to stuff.
If you take the derivative with respect to stuff, you take other stuff.
Yeah. So if the mass is dependent on, say, the theta direction, we still would take them out. Because they have nothing to do with the R. Yeah, minus GM, little m, and then what does this guy become?
Negative 1 over R.
Negative 1 over R. And then we usually have some bounds, unless we want to have plus C.
So that little line is a bound?
So we would go from R to, right, some radial distance R
Not the
to,
radial.
how far do you guys want to go? We're talking about the universe.
6.
How about infinity?
I like that.
There, we go to R to infinity.
We don't know how to do that.
You don't know how to do that?
No.
Sure you do.
I'm sure I don't.
Because one. Yeah, we're
What is equal to U?
Is it U of R or is it U times R?
U as a function of R.
Okay, U of as a function of R.
I'm sorry, Marcos? The two negatives cancel out. G, M, M, and then we have to evaluate this guy, right? So which one subtracts what? I haven't done an integral in a while.
Oh, infinity subtracts the radius.
So the infinity subtracts the radius. Yeah? This minus this? Alright. So we take one, right? We have one piece of pizza. We divide it by an infinite amount of people so that they each get a piece. How much do they get? They get nothing. Alright?
Why does that cancel? Oh, you're
So close to there.
It's so close, we'll just say it's 0. That's a physics trick, okay? Later on, you guys are going to use Taylor expansions. You'll have all these terms. You'll say, after we expand it, that's like 0, and then you just erase stuff. Okay? Magic. All right, so then we have minus GMM over R. And that's our potential energy, okay?
Wait, how is it?
Has the entire thing been on the board?
Yeah.
This entire time?
Just wanted to show you where it came from. And so this, hopefully this makes sense. What we're saying is, if I have a massive object, let's say the Earth, and I move out to a radius that is infinitely far away, you pretty much have zero potential energy with respect to that object. If it was the other way around, it'd be really weird.
Wait, so that's potential energy due to gravity?
Due to gravity.
Oh,
this is the force.
yeah.
Okay, so this is the force. This is. They look almost the same, but there's a negative. And this guy's with respect to this regular 1R, not R squared.
So what would the kinetic be? And when would you use the potential energy?
If it's falling.
You're out there.
If a planet starts falling,
So two objects.
it's a Mr. Vargas. Are we like, is the Earth like constantly falling down?
The Earth is constantly falling towards the sun, but we have such poor aim that we keep missing it.
It's like,
And we've missed it for about 13 billion years.
will it eventually hit the sun?
No, the sun will eventually hit us.
Wouldn't that be because